Today we're going to talk about something called the hyperbola, and it's something you may have encountered in your math classes, especially in PreCal, and for many it can be a point of confusion. And while many of us are very accustomed to the normal functions of a circle, of an ellipse, and even a parabola, hyperbolas are sometimes a bit more complex, but they can also be a lot more fun. In fact, all of these have the same characteristic of being a conic section. So what is a conic section? Well, it's the thing that links all these together, as I've said before, and we can represent them as being simply intersections of a conic, well, two conics, by a plane. And so for our purposes, we'll draw these conics with bases for an ease of representation, and normally these would be identical, and they would extend onwards to infinity. And for this, however, we'll keep them to this limited span. And so what these conic sections are actually formed are when the planes are intersecting this actual conic section that we drew. In fact, in order to get a conic section, it is formed by the new face that is formed when these planes cut through these cones. And so for our example, we see that we've created a face here and a face here. Representing this on a 2D scale, we see that, well, we draw our graph, right? And we can draw this out, and we see that, well, that's interesting. This intersection has two, right? And so perpendicularly, they form this graph. And this graph is precisely what we know as the hyperbola. Well, we found out how we can represent it and its relationship to the other functions we already know. However, in our case, we have to go a little bit deeper. In fact, what a hyperbola is, you have to understand, is characteristically defined by the asymptotes. Unlike the other functions we've talked about earlier, the hyperbola is defined by the asymptotes of a straight line passing through the origin. And while my drawing isn't perfect, these lines would extend onto forever, and so will the hyperbola, infinitely getting closer and closer to the actual asymptote, never actually touching it, because, well, that's the definition of an asymptote. And so, from our previous equations of a circle, which is x squared plus y squared equals r squared, and an ellipse, we can see the relationships of a hyperbola and how we can translate that to something we already know. Well, we see that equals 1, right? And so in these cases, they can both be translated by a constant in this x and y, but in the case of an ellipse, it's something different. And this exact property is what we can use to define our hyperbola. So when defining a hyperbola, we can say that, well, hey, look, we see that there's no points possible on the x-axis, right? These no points are intersecting the x-axis, rather. And so what does that tell us? Well, since a hyperbola must have the same nature of equaling 1, well, a hyperbola has to be subtracting something, because in this case, it wouldn't matter. Both intersect. However, for this, if I draw it out, maybe it could become a little clearer. We see that, a squared minus y squared over b squared equals 1. And so in this case, we see that hyperbolas have a unique function where their one axis becomes unusable, essentially. And so for this function, we see that the x can never be 0. Thus, if the x is 0, this whole portion would get removed because it would equal to 0, and this negative value would become equal to 1, which it isn't. And so it becomes an untraceable point. And so for functions like this, we see a different graph, a type of hyperbola with a unique shape. And for this, we can say that, Well, if we look at the shape, this one can never have an x of 0, right? It can never have an x of 0, and thus it'll never touch this line. It'll never intercept with the y-axis. However, for this graph we drew previously, well, that's a different case. In that case, it would be y squared over b squared minus x squared over a squared. Why? Well, if we understand, y can never be 0, right? And thus, in this case, if y were to ever be 0, this would also be 0, creating an unequal equality. And so, in this case, this function, this up and down hyperbola, relates to the y squared over b squared minus x squared over a squared equals 1. Conversely, we see that this one, where it intersects the x-axis, is by this function right here. And so, using this knowledge we are equipped with, we can solve some equations that involve hyperbolas. And we see how it's useful in the modern world. And so, how is a hyperbola useful? Well, it's a question that almost every student asks. Why is this something important? Well, depending on what you go into, a hyperbolic cooling tower might be your field of study. And for many, a hyperbolic cooling tower might sound like a lot of chemical engineering jargon, but in reality, it's just a mathematical shape that we can represent in the real world. And so here's a picture of a hyperbolic cooling tower if you needed to conceptualize it. And our question gives us a few parameters which we can draw out. A hyperbolic cooling tower is 100 meters wide, so 100 meters wide at the base. And at most narrow section, meaning the point that we previously saw, right, the point where they are the closest right here, we can see that the question is saying they're 40 meters apart. 40 meters apart, and the total point where they're the closest is 100 meters above the ground. How wide is the cooling tower at its highest point when it's 160 meters above the ground? And so that might seem a little confusing. So we draw a picture. And in drawing this picture, we can start off with, well, the ground. And starting up, and we draw our tower, right? Doesn't have to be perfect. In fact, I'll redraw that part. And see, drawing this tower, we see that, well, we have our ground, and we know that this is 100 apart, right? And this is 40 apart because it's the narrowest, right? 40. And then we've realized that this is 100 tall because it's 100 meters above the ground, right? 40 meters wide at that point. And then how wide is the cooling tower at its highest point? 160 meters above the ground. So if it's 160 meters, right? 160 meters. If this point, we're trying to find the width, right? So it's important to find what you're solving for, right? Well, if we understand this, everything on a plane, in fact, if everything is drawn on a plane, it becomes easy. This becomes a point, this becomes a point, everything becomes a point that we can calculate for if given an equation. And so let's draw our plane, right? Let's draw our plane in which we can calculate things off of. And so if we set the origin exactly where we've set the other parabolas at, like in the previous example, right here, if we set the origin there, this doesn't necessarily have to be a mirror reflection, but it follows the same rules of hyperbola, meaning it follows the function. And so in this case, what do we see? Well, keep using our formula for this one. What do we see? It intercepts the x-axis but not the y. And so the formula we use is x squared over a squared minus y squared over b squared equals 1. And so this is the important formula that we can use to solve this question. And what do we find first? Well, for these types of questions, a squared is the easiest to find because it already gives you the width at the narrowest point, the width where these two are the closest. And so that means because we set our origin here, right? Because we can translate this anywhere on the graph where we want to. I could have put it down here, up there. Because we put it here, it becomes easier to solve. And the fact that, well, at this point, we know that y is 0, right? And so for this calculation, it becomes easier to isolate the a squared, because we can write this as x squared, a squared, minus 0 squared, right? 0 squared over b squared equals 1. And so when writing like this, it becomes easy to see, well, obviously this is 0, so then it just becomes a matter of a squared over, x squared over a squared equals 1. And so in this equality, we've proven by substituting the values we were given, by the placement at the origin. And so we know that this point right here is equal to, well, half the width, which is 20 right here. That means that this point is equal to 20, 0, right? So that means the x value at this point we're calculating for in order to isolate a can be 20. And so that means this equals 20 squared over a squared. And so, 20 squared over a squared, yes. So this equals 1. Going on with algebraic calculations, we can see we can rearrange everything. 20 squared equals a squared. When we multiply both sides by a squared, this 1 multiplied by a squared is a squared. So having found a squared, we've made an important step towards solving this, because now we can put it back into the equation and start solving for b squared. And so x squared over 20 squared, we'll keep it 20 squared for the sake of simplicity, right? Minus y squared over b squared equals 1. And so in this case, how do we isolate the b? How do we solve for b? Well, let's try rearranging the terms. And so in doing this, we first start off, let's put this back to a. We can solve for these values later, right? Because we've already solved them here. So x squared over a squared minus y squared b squared equals 1, right? And so here, well, it becomes obvious. Well, we can, in fact, subtract x squared from both sides. X squared over a squared from both sides. Subtracting x squared from a squared over a squared from both sides gets us this result. Y squared over b squared equals 1 minus x squared over a squared. And so from here, right, we've reached an important step. From here, we can, well, divide everything by negative y squared. Dividing everything by negative y squared, and we can take these calculations a little bit lower, right? And so dividing everything by negative y squared, we can get 1 over b squared equals 1 minus x squared over a squared divided by negative y squared. And so these negatives cancel out, and this becomes a negative, and so we can rearrange it as 1 over b squared equals x squared over a squared minus 1 over y squared. And so since we don't like reciprocals, and for the sake of simplicity, we can turn this reciprocal into something easier and write simply b squared equals y squared over x squared over a squared minus 1, right? Extend that out a little bit. And so for the sake of simplicity, we can plug any point into this equation and find b. So having solved for a, we can plug in b squared equals some value, right, we want to use, and some value of x we want to use over the 20 squared minus 1, right? So going back up to the problem, well, what do we know? What point can we use? So since we've already defined the origin here, the cooling tower is 100 meters wide at the base. So okay, it's 100 meters wide, and if the origin is here, the y-axis is here, that means this distance is 50, right? And so if this is 50, then it means, and if this height from center point that we've defined here is 100, then we can say that, well, this point is 50, negative 100. And so while that may seem confusing, as long as you remember to put your origin here, exactly at the point of the nearest point, well, you see clearly that this point is below the origin, right? 100 below, because we're given the height at that point, and it's also 50 away because we've placed the origin directly in the center. And so moving down, we can use this points, 50 and negative 100, right? And so you're plugging in 50 for x, right? At this point, it doesn't matter for negatives because it's being squared, 50 and 100 for y, right? We solved this out. For the sake of time, I've solved it out already. B squared, right? B equals the square root of b squared, right? B would equal to, B is equal to 43.64358. And you're like, why is this a decimal? Why is it so complicated? Well, you see that hyperbolas oftentimes don't follow very strict rules when given specific real-world heights like the ones above the problem. And so it's important that we keep the precision that we have here. And so we found B, we found A, and now we can go back and look at the actual problem. We can go back and look at the problem. What do they want us to solve? The highest point, 160 meters above the ground. What is the width? Well, we have our B, we have our A squared, and so in this case, we can find that, well, plugging everything in, we can see that the only thing we're missing is what? X, right? Because we're finding width. The only thing that's missing is x. So we can just plug that in to the equation. So going off our normal hyperbola equation from the characteristic we've defined here, x squared over a squared, which is 20 squared minus y squared. So we know our y because y, well, it's 60 above our origin that we previously defined, right? 60 above, and so we can just put y as positive 60. 60. Sorry, I can't write today. 60 squared over b squared, and so that's the number we found over here, right? So squaring that, 43.64358 squared equals 1. And so for the sake of time, you can put this into a calculator, a graphing calculator, and see how this actually plots out in a real graph. But for the sake of time, I've already solved for x, and our x value is 34. You see how this works out? While it may have some minuscule decimal imprecision, this decimal value is very important in finding the calculation for x. And so we found x. We found x. I previously calculated it. However, it's asking for the width. The width, how wide it is at the cooling tower at the highest point, right? We found the x value, right? We found the x value. However, we haven't found the width until we've doubled it. And so in doubling it, it's a simple matter of multiplying by 2. And multiplying by 2, multiply that by 2, we get, well, 70, no, not 70, 68. 68 meters across. And so we've solved by using plotting points, transformation of hyperbolas using the identity and the shapes and characteristics of hyperbola, isolating a squared and b squared, we've found a function to define a specific hyperbola given points that we can plot, and found another point given one value in the coordinate pair. And so our answer to this problem is 68 meters across. And so in this lesson, we've covered hyperbolas, what makes them up, and how to solve real-world problems regarding them. I hope you enjoyed this, and thank you.